The first key to enhancing performance and learning through a growth mindset is interpreting challenges as opportunities rather than threats, which fundamentally shapes how the brain responds to difficulty. When the brain encounters a challenging task, it rapidly assesses the situation through the interplay of the prefrontal cortex and limbic structures, particularly the amygdala. The amygdala signals potential threats, triggering stress responses that release cortisol and other stress-related neuromodulators. In a fixed mindset, the brain interprets challenge as a reflection of personal limitations or identity, activating avoidance circuits and reducing cognitive flexibility. This leads to impaired working memory, limited problem-solving capacity, and a diminished ability to engage with complex tasks. In contrast, a growth mindset reframes challenges as signals for neural adaptation, allowing the prefrontal cortex to maintain executive control and coordinate strategies for learning. This reframing alters the neurobiological response to difficulty. Instead of triggering an overactive stress response, the brain interprets challenge as informative feedback about current skill levels. Dopaminergic circuits in the striatum and prefrontal cortex are engaged when progress toward mastery is detected, even if the goal is not fully achieved. This dopamine signaling reinforces goal-directed behavior and encourages sustained engagement. In essence, the growth mindset creates a neural environment in which challenge is associated with potential reward rather than punishment, increasing motivation and the likelihood of repeated effort. Perception of challenge also interacts with attentional systems. The locus coeruleus norepinephrine system, which regulates arousal and attention, responds differently depending on the perceived threat or opportunity of a task. In a fixed mindset, excessive norepinephrine release due to perceived threat can narrow attention, focusing the brain on potential failure rather than learning. In a growth mindset, challenge-related arousal is balanced, enhancing alertness and facilitating broad attentional deployment, which is critical for integrating new information, problem-solving, and adaptive decision-making. Repeated exposure to challenges in a growth-oriented framework further enhances neuroplasticity. Each time the brain successfully navigates difficulty, synaptic connections in circuits associated with executive function, learning, and resilience are strengthened through long-term potentiation. The prefrontal cortex and hippocampus in particular consolidate these adaptive changes, improving both cognitive control and memory encoding for future tasks. Over time, the brain develops a predictive model that associates effortful engagement with positive outcomes, making it more likely that subsequent challenges will be approached proactively rather than avoided. Behavioral strategies reinforce this neural process. Approaching difficult tasks incrementally, setting specific sub-goals, and reflecting on progress provide consistent feedback that the brain can encode as meaningful signals of growth. These strategies also reduce the emotional salience of potential failure, keeping stress responses within an optimal range for learning. Social cues, such as mentorship or collaborative problem-solving, amplify this effect by providing external validation and modeling adaptive approaches to challenge, further shaping neural circuits related to engagement and resilience. By interpreting challenges as opportunities rather than threats, the brain engages circuits for learning, attention, and adaptive problem-solving while minimizing maladaptive stress responses. This key establishes the foundational mindset that determines how all subsequent experiences, feedback, and efforts are processed, ensuring that difficulty becomes a me. The second key to enhancing performance and learning through a growth mindset is embracing errors as learning signals rather than indicators of failure. Errors are not just accidental outcomes. They are critical neurobiological events that provide the brain with information about mismatches between intended actions and actual results. The anterior cingulate cortex, ACC, plays a central role in detecting these discrepancies, signaling the presence of errors and initiating adaptive adjustments in behavior. When mistakes are framed positively as opportunities to refine strategy and skill, the brain's response facilitates learning rather than discouragement. In individuals with a fixed mindset, errors are often interpreted as threats to self-concept, triggering amygdala activation and stress responses that release cortisol. This physiological stress can impair cognitive flexibility, limit working memory, and increase avoidance behaviors. In contrast, a growth mindset reinterprets errors as informative signals that highlight areas where neural circuits require further strengthening. This reframing reduces the emotional load of mistakes and allows prefrontal regions responsible for executive function to remain engaged, promoting problem-solving, planning, and adaptive learning. Dopaminergic circuits are also deeply involved in how errors influence learning. When an individual perceives an error as an opportunity to improve, dopamine signaling in the striatum and prefrontal cortex reinforces attention to corrective actions rather than avoidance. This process strengthens synaptic connections in circuits associated with task performance, learning, and skill acquisition. Over time, repeated engagement with error-driven learning enhances predictive coding in the brain, allowing for more accurate anticipation of outcomes and more efficient behavioral adjustment in future tasks. Error processing also interacts with the hippocampus, which encodes experiences and contextual information into memory. By integrating errors into memory as opportunities for adaptation, the brain creates a rich database of experiences that can guide future behavior. Reflecting on mistakes and extracting lessons reinforces this encoding, ensuring that errors do not simply exist as negative experiences but become instructive inputs for ongoing skill refinement. This process underlies the concept of deliberate practice, in which focused effort on challenging, error-prone tasks drives expertise through repeated correction and refinement. The framing of errors is critical for emotional and motivational reinforcement. Positive emotional engagement with mistakes, such as curiosity or problem-solving excitement, amplifies learning by increasing synaptic plasticity through neuromodulators like dopamine and norepinephrine. In contrast, negative emotions such as shame or frustration can suppress these plasticity mechanisms and inhibit long-term retention. This is why mindset and emotional interpretation are inseparable from the process of learning from errors. Behavioral strategies further support this neural framework. Breaking complex tasks into smaller steps allows for more frequent, manageable errors, creating a continuous feedback loop that promotes learning. Additionally, external feedback from mentors, peers, or performance metrics provides structured information that the brain can encode and use to adjust strategies. Combining internal reflection with external guidance ensures that errors are interpreted constructively and integrated effectively into neural circuits. By embracing errors as learning signals, the brain converts mistakes into catalysts for growth rather than threats to identity. This key enables adaptive learning by maintaining engagement of executive networks, reinforcing dopaminergic pathways, and consolidating error-driven memory. It ensures that setbacks are not endpoints, but rather essential components of the process by which performance improves and skills are refined. The third key to enhancing performance and learning through a growth mindset is valuing effort as a primary driver of neural change. Effort is not merely a demonstration of willpower or perseverance. It is the mechanism through which the brain's synaptic networks are strengthened, refined, and optimized. When the brain engages repeatedly in challenging tasks, neurons involved in the relevant skills fire together, strengthening their connections through long-term potentiation. This is the biological basis of learning, where effortful practice directly modifies the structure and efficiency of neural circuits, gradually converting intentional actions into automatic, skilled behaviors. The prefrontal cortex plays a central role in this process by orchestrating effortful behavior, sustaining attention, and integrating feedback. When an individual applies deliberate effort toward a complex task, the prefrontal cortex coordinates multiple brain regions to maintain focus, inhibit distractions, and execute strategic actions. Simultaneously, subcortical structures, like the basal ganglia and striatum, encode repetitive action patterns, gradually transitioning behaviors from effortful conscious control to habitual automatic execution. A growth mindset emphasizes that effort itself is productive because it directly engages these neural systems, reinforcing learning at the structural and functional levels. Dopamine is another critical factor in the relationship between effort and learning. Dopaminergic neurons in the ventral tegmental area and nucleus accumbens signal progress, reward, and motivational salience. When effort leads to observable improvement, even incremental, dopamine release reinforces the neural circuits associated with that effort, enhancing both motivation and retention. This is why consistent effort, even in the absence of immediate external rewards, produces sustained engagement and drives long-term skill acquisition. Effort becomes intrinsically rewarding, linking action directly to neuroplastic changes in learning circuits. Effort also interacts with the brain's executive control networks to regulate error processing. The anterior cingulate cortex monitors discrepancies between intended and actual outcomes, signaling areas for adjustment. When effort is applied consistently, errors are interpreted as opportunities for refinement rather than failures, engaging prefrontal striatal circuits that support adaptive learning. This combination of sustained effort and constructive error processing ensures that the brain continuously optimizes strategies, consolidates successful behaviors, and integrates new skills into existing neural networks. The concept of deliberate practice illustrates this principle. High-quality effort involves focusing on tasks that push the boundaries of current ability, creating repeated opportunities for neural circuits to be activated in novel ways. This targeted activation strengthens connections more effectively than routine or unchallenging practice, maximizing neuroplastic adaptation. Importantly, the perception of effort is influenced by mindset. Individuals with a growth-oriented perspective interpret effort as productive and meaningful, which enhances engagement and increases the likelihood of sustained practice. Environmental and contextual factors can amplify the effectiveness of effort. Structured routines, supportive environments, and access to feedback create conditions in which sustained effort is easier to maintain. The brain encodes these repeated actions more efficiently when the context minimizes distractions and provides clear cues for behavior. Social reinforcement, such as recognition or mentorship, further enhances the dopaminergic and emotional signals associated with effortful engagement, strengthening the neural pathways that underlie skill development. Valuing effort also shifts the focus from outcomes to process, which is critical for long-term performance and learning. When individuals prioritize the effort itself, neural circuits associated with sustained attention, problem-solving, and adaptive control are consistently engaged. Over time, this repeated activation consolidates learning, expands cognitive capacity, and transforms the brain's predictive models of performance. In this way, effort is not just a means to an end, but a fundamental driver of neuroplasticity, motivation, and the ongoing development of skills and identity. The fourth key to enhancing performance and learning through a growth mindset is leveraging feedback constructively, which is central to how the brain refines skills, adapts behavior, and strengthens neural circuits. Feedback provides information about the discrepancy between intended outcomes and actual results, allowing the brain to adjust predictions, correct errors, and optimize performance. The anterior cingulate cortex plays a pivotal role in detecting these discrepancies, signaling the need for behavioral modification, while the prefrontal cortex orchestrates planning and decision-making to implement corrective strategies. When approached with a growth mindset, feedback is interpreted as actionable information rather than a judgment of innate ability, creating conditions that maximize learning and neural adaptation. The brain's response to feedback is highly dependent on context and emotional framing. Negative feedback, if interpreted as a threat, activates the amygdala and triggers stress responses that impair cognitive flexibility, working memory, and problem-solving capacity. In a fixed mindset, this can result in avoidance, defensive reasoning, or disengagement, limiting opportunities for learning. A growth-oriented approach, however, reframes negative feedback as a signal for improvement, engaging the prefrontal cortex and striatal circuits in a way that promotes adaptive behavior. Positive feedback, meanwhile, reinforces correct actions through dopaminergic signaling, strengthening the neural circuits associated with successful strategies and increasing the likelihood that those behaviors will be repeated. Feedback also enhances predictive coding, the brain's mechanism for anticipating outcomes based on prior experience. By comparing expected and actual results, the brain updates its internal models of action and skill execution. This process involves the hippocampus, which encodes contextual information, and the basal ganglia, which integrate repeated patterns of action and reward. Constructive feedback ensures that these circuits are refined efficiently, accelerating skill acquisition and improving performance over time. The more consistently feedback is applied and interpreted as informative, the more the brain's predictions become accurate and the less effort is required to achieve desired outcomes. Timing and specificity of feedback are critical factors for optimizing learning. Immediate targeted feedback allows the brain to associate specific actions with their consequences, facilitating precise adjustments to neural pathways. Delayed or vague feedback is less effective because the brain struggles to link outcomes to particular behaviors, reducing the efficiency of synaptic strengthening. Structured practice routines that incorporate regular focused feedback provide repeated opportunities for error detection, correction, and reinforcement, ensuring that neuroplastic changes are robust and long-lasting. Emotional engagement further amplifies the impact of feedback. Feedback perceived as meaningful, relevant, and achievable triggers neuromodulators such as dopamine and norepinephrine, which enhance synaptic plasticity and memory encoding. This means that the way feedback is framed, emphasizing progress, potential, and actionable steps, directly influences how effectively the brain integrates the information into learning circuits. Conversely, feedback framed as judgmental or evaluative can increase stress-related cortisol release, suppressing plasticity and reducing engagement. Social and environmental factors also modulate how feedback affects performance. Mentorship, peer review, and collaborative learning environments provide diverse and repeated feedback, reinforcing adaptive circuits through social and emotional salience. Observing others' performance and receiving feedback in a socially meaningful context enhances mirror neuron activity and reinforces learning through vicarious experience. Additionally, external feedback systems, such as tracking metrics or performance dashboards, provide objective signals that the brain can integrate into ongoing neural computations. By leveraging feedback constructively, individuals engage neural mechanisms that detect errors, refine strategies, and reinforce successful behaviors. This key ensures that learning is not accidental but systematically guided, allowing neural circuits to adapt efficiently, skills to improve consistently, and performance to reach higher levels over time. Feedback, when interpreted through a growth mindset, becomes a powerful tool for neuroplasticity and sustained achievement. The fifth key to enhancing performance and learning through a growth mindset is utilizing neuroplasticity through consistent practice, which is the fundamental mechanism by which skills are developed and mastery is achieved. Neuroplasticity refers to the brain's ability to reorganize itself by forming new neural connections and strengthening existing ones in response to experience and learning. This process allows the brain to adapt to new challenges, integrate novel information, and improve efficiency in executing tasks. In the context of a growth mindset, neuroplasticity is actively harnessed because the individual views effort, challenge, and learning opportunities as stimuli that can reshape the brain rather than fixed limits on ability. Repeated activation of neural circuits is central to neuroplasticity. Every time a behavior or cognitive strategy is practiced, the involved neurons fire together, increasing synaptic strength through long-term potentiation. Over time, these strengthened circuits become more efficient, allowing the behavior or skill to be executed with less conscious effort and greater precision. For example, consistent practice of a complex motor task not only enhances motor cortex efficiency, but also engages basal ganglia circuits that automate sequences, reducing cognitive load. Similarly, repeated cognitive practice, such as problem solving or learning new concepts, reinforces prefrontal networks involved in attention, working memory, and executive function. Deliberate and targeted practice amplifies neuroplastic changes. Random or unstructured repetition is less effective because the brain requires challenge and error-driven learning to identify which circuits need adaptation. In a growth mindset framework, practice is deliberately focused on areas that push the limits of current ability, generating a controlled amount of difficulty. This activates learning-related circuits in the prefrontal cortex, anterior cingulate cortex, and striatum while providing feedback that guides the refinement of neural pathways. Each repetition strengthens relevant connections while weakening unused or maladaptive circuits, optimizing brain function for the task at hand. Sleep and recovery are also integral to neuroplasticity. During sleep, particularly slow-wave and REM phases, the brain consolidates new neural connections, integrates experiences into memory networks, and stabilizes synaptic changes initiated during practice. This means that consistent practice coupled with adequate rest ensures that neural adaptations are durable and efficiently integrated into broader cognitive and motor systems. Without proper consolidation, repeated practice alone is insufficient to produce lasting changes. Motivation and emotional engagement further influence neuroplastic outcomes. Dopamine release during successful or progress-oriented practice signals the importance of activated circuits and enhances synaptic strengthening. A growth mindset enhances these signals by framing effort and challenge as meaningful and rewarding, ensuring that repeated activation of circuits is both frequent and reinforced. Emotional salience, such as curiosity, excitement, or satisfaction with improvement, increases attention and enhances memory encoding, making the practice more effective at reshaping neural networks. Feedback mechanisms interact with neuroplasticity by providing the brain with information to fine-tune circuits. Each error or success during practice helps the anterior cingulate cortex and prefrontal networks detect discrepancies between intended and actual outcomes. Corrective adjustments are then encoded into synaptic connections, allowing skill execution to become progressively more accurate. Over time, repeated cycles of practice, feedback, and adjustment create highly efficient neural pathways, converting effortful performance into automatic competence. Environmental consistency also enhances neuroplastic outcomes. Practicing in stable, focused, and minimally distracting contexts allows the brain to concentrate resources on strengthening relevant circuits rather than managing competing inputs. Social environments, mentorship, and guided instruction further amplify learning by providing structured feedback and modeling effective strategies, which the brain can encode through observation and imitation. By utilizing neuroplasticity through consistent, deliberate, and emotionally reinforced practice, individuals can systematically shape the brain to enhance skill acquisition, performance, and cognitive flexibility. In a growth mindset framework, neuroplasticity transforms effort into structural and functional neural improvements, making learning progressive, efficient, and sustainable. The sixth key to enhancing performance and learning through a growth mindset is aligning motivation and emotion with progress, which ensures that the brain remains engaged and adaptive throughout the learning process. Motivation and emotion are not just byproducts of learning. They are central drivers that determine how effectively neural circuits are activated, strengthened, and integrated. Dopamine, in particular, plays a critical role by signaling progress, reinforcing behaviors, and enhancing synaptic plasticity. When individuals perceive that their actions are producing meaningful improvement, even incremental dopaminergic pathways in the striatum and prefrontal cortex are engaged, amplifying attention, effort, and memory encoding. A growth mindset influences how progress is perceived and how emotions are interpreted. Individuals who adopt this perspective focus on improvement rather than solely on outcomes, which shifts the brain's reward system to respond to incremental gains rather than binary success or failure. This reframing allows dopamine to reinforce the process of learning itself, making repeated effort intrinsically rewarding. In contrast, a fixed mindset often interprets errors or slow progress as a reflection of inherent limitations, triggering amygdala-driven stress responses that impair attention, working memory, and problem-solving, reducing the efficiency of neural adaptation. Attention is a key mediator between emotion, motivation, and learning. The locus coeruleus norepinephrine system regulates arousal and attentional focus, responding to stimuli that are perceived as salient or meaningful. When progress is highlighted and recognized, the brain allocates more cognitive resources toward task-relevant circuits, enhancing the encoding and consolidation of new skills. Conversely, when progress is overlooked or undervalued, attentional systems are less engaged, reducing the likelihood that repeated practice will translate into long-term neuroplastic changes. Emotional framing amplifies the effect of motivation on learning. Positive emotions such as curiosity, satisfaction, or pride increase synaptic plasticity, while negative emotions such as shame, frustration, or discouragement can suppress neural adaptation. A growth mindset deliberately cultivates positive emotional associations with effort and learning, ensuring that each engagement with a challenging task strengthens the brain rather than creating avoidance patterns. Reflection and self-assessment, when framed constructively, allow individuals to internalize progress, enhancing the emotional salience of improvement and reinforcing adaptive circuits. Goal structuring interacts with motivation to shape learning outcomes. Breaking larger objectives into smaller, achievable milestones creates repeated opportunities for the brain to detect progress, triggering dopaminergic reinforcement at each step. This incremental approach ensures that motivation remains high and that neural circuits are continuously engaged in a pattern of activation, strengthening, and consolidation. Social reinforcement, such as mentorship, peer acknowledgement, or collaborative learning, further enhances the salience of progress, adding emotional and social dimensions to the motivational signal, which the brain encodes as valuable for adaptive behavior. Motivation also interacts with effort and persistence. The perception of progress reduces perceived effort costs, allowing the prefrontal cortex to maintain sustained engagement over longer periods. When individuals experience tangible improvements, they are more likely to persist through challenges, increasing the frequency and intensity of neural activation required for skill acquisition. This creates a positive feedback loop in which effort, reinforced by perceived progress, leads to further neural adaptation and improved performance. By aligning motivation and emotion with progress, the brain integrates cognitive, emotional, and reward signals in a manner that maximizes learning efficiency. This ensures that repeated practice, error correction, and engagement with challenges produce meaningful neural changes, reinforcing a growth-oriented identity. Motivation and emotion act as both fuel and guidance for neuroplasticity, making learning not only more effective but also sustainable and intrinsically rewarding. Ultimately, by aligning motivation and emotion with progress, individuals create a self-reinforcing system in which effort, attention, and learning are continuously rewarded at a neural level. This ensures that the brain remains engaged, circuits are strengthened, and skills are refined efficiently over time. When progress is perceived as meaningful and emotionally salient, it transforms challenges into opportunities, mistakes into feedback, and effort into tangible growth, making the journey of learning and performance sustainable, adaptive, and deeply empowering.